Okay, let us discuss the thermodynamic derivation of law of chemical equilibrium. So we have already noted that law of chemical equilibrium is actually the relations between the K equilibrium, that is the equilibrium constants, and the active masses of the that product, multiplication of active masses of the product divided by multiplication of the active masses of your reactant. Okay, so let us derive this one by using thermodynamic concept. But in the previous class we derived this one by using the law of mass action. Okay, but now we have to use the thermodynamic concept. Okay, so we know that thermodynamically we know that. So because we are going to use the thermodynamic concept to derive that equation, so we have to know some thermodynamic terms. Okay, in the first class we have the idea about the del G. Okay, so what is del G? Del G is your change of Gibbs free energy, and if it is less than 0, we said that the reaction is spontaneous. This is coming in the second law of thermodynamics. Okay, the last part of second law of thermodynamics. Okay, so if that is less than 0, that means if del G is negative, that is del G is negative, then the process is what? The process is your spontaneous. The process is spontaneous process. Okay, if del G is greater than 0, that is positive, then the process is what? Non-spontaneous. Non-spontaneous. Okay, so we know these 2 points. And also the for reversible reactions, we are saying that del G is equal to 0 if the rate of the forward reaction is equal to the rate of backward reaction. That means we're going to use this concept. Okay, here to derive this law of mass action, we have to use this concept, because this concept is for the reversible reactions which forward rate reactions is equal to the backward rate reactions. What is the meaning of this? It is the meaning of it is that the that condition at that condition the reactions will be at equilibrium. Okay, so here, so we're going to use mainly 2 concept. Okay, here it is given, you see. Okay, so before going to discuss about this derive this one, so we need a reaction. Okay, we need a reversible reaction. So let us suppose our reversible reactions is A mole of A, B mole of B will going to react with each other, and they will going to form M mole of M and N mole of N. Okay, so this is number of mole. Okay, number of moles of A, number of moles of B. Okay, so I think you understand this one. Okay, so suppose this is your reactions, and let's suppose the all the reactants and the products are in gaseous state. So they all are in what? They all are, these 4 are in gaseous state. Gaseous state. Okay, US state, in gaseous state. Okay, so we have that one reaction, reversible reactions, and we have also the idea. So what idea we have to going to use? We are going to use the del G is equal to 0 idea. Okay, but alone it will not going to help you to derive the equation. We need actually more idea about the thermodynamics. Okay, so here actually it is given, you see, in this part 2 concepts are given. Okay, so the first concept is that one we have already studied this one, or we discussed actually. Del G is equal to 0. Okay, so we already know that del G must be 0 for reversible reaction. So if you are talking about reversible reactions, that means del G is always, and if it is at equilibrium, reversible reaction, and if it is at equilibrium, then the uh, del G must be equal to 0. So actually this part should be, this del G is equal to 0 for reversible process at equilibrium state. Okay, you have to add here at equilibrium state. Okay, at equilibrium state. So you have to correct this one. Okay, and number 2 is that G is related to this, Gibbs free energy is related to chemical potential. So what is chemical potential actually? Chemical potential is actually defined as it is denoted by mu. Okay, and for a component I, any component, okay, and component I, it is actually defined as the change of Gibbs free energy with the numbers of moles of that I. That means if we add, or if we change the uh, you know uh, amount of that component I, then how much Gibbs free energy will going to change. That is your chemical potential. Okay, but it is, their condition is at, it should be at constant temperature, and it should be at constant pressure, and the other component must be at same concentration or at same composition. Okay, so that means J does not equal to I, so this should be constant. Okay, so this is your definition of chemical potential. Okay, so chemical potential is actually the change of Gibbs free energy. That means it is very simple. Okay, if let's suppose this is a beaker, so if you add some, let's suppose here A and B are present. Okay, okay, so if you add some more A in this mixer, then how much Gibbs free energy will going to change. Okay, that is your chemical potential of A. So that means if you add A in a solution where A is present and also a B is present. Okay, if on the addition of that A will going to change their Gibbs free energy, then the amount of change of Gibbs free energy due to the addition of that number of moles of A is known as the chemical potential of component A. Okay, and the condition is that the temperature of that system must be temperature, pressure, and the other composition, that means B should be constant. Okay, this is the physical meaning. Okay, so this is your chemical potential. So we have the second idea that G is related to chemical potential, and chemical potential is known as for I is already we know that del G is d by dni. Here temperature and pressure is constant, and n J does not equal to I. Doesn't equal to I means this n should, the constant n should be, that means the other components should be constant, uh, and the other components is not I. Okay, so this is your relation. So we're going to use mainly this concept number 1, and we're going to use the definition of this one also, because again here you see, since del G is equal to 0, that means Gibbs free energy since is equal to 0 for at equilibrium, at actually equilibrium, at equilibrium for a reversible process. So since this one is directly related to this one, then what we can say, we can say that even that chemical potential change would be also 0 at equilibrium, uh, in equilibrium reaction at actually at equilibrium position. Okay, at equilibrium position. So now we're going to derive the relation, okay, by using this two. So So we have what? We have that reaction. Reaction is what? A, B will going to react with each other, and they will going to form M mole of M and M mole of N. Okay. So now again, simply this can be also written as like that. Okay. G is equal to A mu A. This is for A. So this is for GA. So GA for A, because mu is equal to what? Actually mu A is equal to your dg by dA, because A is number of moles. So here dg is equal to mu A, dg is equal to mu F into dA. So this is actually the sense. If you know that, you can also write this one mu A. So that means in place of in place of G, you can write mu A into A. That means so we're going to use this technique. Okay. So here you have this reaction. So these are what? These are your reactant, and this is your product. Okay. This is your reactant and this is your product. Okay. So coming to the next slide. Wait. Okay. So okay, so we have these reactions, and this is your reactant, these are your reactants, and these are your product. So we know that del G is equal to 0, okay, for at equilibrium position. Okay, so del G is what? Del G is equal to del G product minus G reactant. Okay, again G is related. G can be written as mu A into A. Okay, for A, this is GA. Okay, GA is equal to mu A and A. So we can write here for products. Products are two products are there. So what we can write for first one, we can write M mu A plus second one for this product N mu N. Okay, so this is for product minus A mu reactant A. So here it should be M. Okay, A plus B mu B. So we have this one, no? So we can simplify this one. Actually just make this one as 1. Okay, just just make this one 1. Okay, and this relation, but here it should be 0. Okay, 0, and it should be also 0. Okay, so this is your number 1 equation. Okay, so again actually mu, actually this chemical potential can be defined as mu I naught, where this is for standard case. Okay, standard chemical potential, and plus RT ln pi. Since we are talking about gases now, so we have to consider the pressure. Okay, because one gas can be actually we can characterize, or we can tell their state of a gas by knowing their pressure. If the pressure is high, then their energy state will be high. Okay, so this is your first equation, and this is your second equation. Actually this is, you have to remember this one. Okay, mu I is equal to mu plus RT ln pi. Okay, this is also the second relation, and this is your first relation. So we're going to use this relation to get our law of chemical equilibrium. Okay, so these two are very important. So now what you have to do, you have to just Here we have from equation 1 and 2, what we can write? Equation 1 is what? Equation 1 is your m mu a mu m. Again, this is, you should right here, is it m? Okay, mu m plus n mu n bracket minus a mu a plus b mu b is equal to 0. Okay, so we can insert this equation here. Okay, so here m, but in place of mu a, what we can write? Mu m naught plus rt ln p, and this is your m, because in place of I, just you have to put the value here. In here m is here, so you have to put m. For this one you have to put n. For this one you have to put a. This one b b b, a n n n, m m m. Okay, so like that. So this is your n mu n naught plus rt ln pn. Okay, so this is your bracket, and this is done. This part is done. Then minus this reactant part will be a mu a to the naught plus rt ln pa plus b mu b naught plus rt ln pb. Okay, so actually this is equal to 0. So second part is also done. So now what if you have to just simplify these two, actually this equation. So if you simplify these relations, then you will get rt ln pm to the power m, pn to the power n, pa to the power a, pb to the power b. Okay, so this is actually partial pressure for the component m. This is the partial pressure for n, and this is for partial pressure for a, and this is partial pressure for b. So this is t is equal to, actually if you minus, if you solve this one, then it will get this one, you will get this one. Okay, m bracket m mu naught m plus n mu n naught minus a mu n naught plus b mu b naught. So what is this actually? These are actually this is actually chemical potential of actually this is chemical potential of your product, and this is reactant. This indicates, and if you multiply the chemical potential with the number of moles of that particular component, then you will get the Gibbs free energy. Okay, that means this is actually the Gibbs free energy of your product, and this is your Gibbs free energy of your reactant. So in place of this whole thing, what we can write? Gives these things, we can write this from here to here, we can write G product, and this is for G reactant. Okay, so just write this one. Okay, so what we can write? Pm to the power m, a to the power a, b to the power b is equal to minus G. So here we have to close the bracket. Okay, you have to write this bracket and here, because this is your standard case now, so you have to write here also standard. G standard product. First part is product, and second part is G naught reactant. Okay, so we have that equation. So now again, rt ln pm to the power m, pn to the power n, pa to the power a, pb to the power b is equal to, and what is this actually? This indicates what? This is actually minus, actually this is gives free energy since of product, that is the gives free energy at its standard condition product minus gives free energy at standard condition for reactant is actually the change of gives free energy at standard conditions. That is actually the reaction. gives free energy for your reaction. Okay, so here actually I forget to write the negative signs. Okay, so you have to write here this part, one negative should be here. Okay, so please write the negative here, here. Okay, here it should be negative, one negative. Okay, so it will be your negative reactant. Now what you can write, we can just write PMM PNN PAA PBB is equal to here RT na, so it will be like minus del G not reaction divided by what, your RT. So this part will go there na? So ln will be what, here ln is there na, so ln will be here. So but if you multiply with e, then this e will cancel this ln, and here you have to write e, that means exponential. Okay, so it is your exponential to the power this one. So that means what you can write, so let's write this one properly. So you have these relations now you have these relations pm to the power m pn to the power n divided by pa to the power a pb to the power b is equal to e to the power minus del z naught reactant, sorry, reactions. And you can also omit this one. Okay, reaction part r t. So if you want to write, then you can write here reaction, and you can even omit this one. Okay, here it is actually written here, is it? It's actually this one. Okay, this part, sorry, not this part, from here to here. Okay, so this is your actually the relation. So up to this I think you understand. Now from this we're going to uh, derived our law of chemical equilibrium. So here it is okay, up to this it is okay. So here, but if you notice this one, this del G is actually the Gibbs free energy of that reaction at a standard state. Okay, at a standard state, and this is actually constant for constant temperature. If the temperature is constant, then del G will not going to change. That means del G is actually depends upon only the temperature, not del G not. Okay, that means gives free energy at a standard state. Okay, or standard condition. And R is all, we know that R is the gas constant. It is always constant, 8.313, and this is T. T is already, we assume that temperature is constant, so T is constant. If T is constant, then del G naught is also constant, and R is already is constant. So that means e to the power minus some constant is always constant. This is already constant. So that means P m to the power m small p. Okay, Pn to the power n, P to the power f, Pb to the power b is equal to constant. And actually okay, wait, so this is your constant. Actually this constant is your the Kp, that means the equilibrium constant, but this here we just write P because we are considering here what, pressure. Okay, because this is your gaseous reactions now. So this Kp indicates, or Kp denotes the equilibrium constants for gaseous reactions. Okay, where we measure the pressure to define that state of that gas. Okay, so that means Pm to the power m, Pn to the power n, Pa to the power a, Pb to the power p is equal to Kp, and this is your the law of chemical equilibrium. So this is your law of chemical equilibrium. Okay, so I will going to send you the PDF. Actually you can find the PDF in the description part of this video. so YouTube video, so you can go to the description, and there I will going to attest this PDF, so you can even download from there. Okay, so this is the law of chemical equilibrium for gaseous reactions. Okay, so this is for gaseous reactions. What about the other reactions, solutions? If it is liquid, then what will going to happen? So let us discuss about them. Okay, so here similarly, you see here similarly, actually, for if if you wait, okay, it is okay. So similarly, um actually mu I is equal to mu I naught plus RT ln xi. Just we can replace the pressure by the, this is the mole fractions. If you consider the mole fractions, if you are able to calculate the mole fractions for a reactions, or the mole fraction of the reactants and the product, then you can replace the pressure uh, by the mole fractions. And if you replace this pressure by mole fractions, then the final reaction, final actually the law will be like this form. Okay, in place of pressure you have to just write, so what we have already p m to the power m p n to the power n divided by p a to the power a p b to the power b is equal to what, your k p. It is already derived now by using the thermodynamical concept actually. So in place of this pressure here, you see, if we can replace this pressure by xi, that means the mole fraction. If you can calculate mole fractions, then we can replace this one. Okay, so we can easily replace. Okay, so just in place of p, what we have to write, we have to write the x, that means the mole fraction. So we can write here x m to the power m, x n to the power n divided by x a to the power a, x p to the power b is equal to k. But here in place of p we can write c. Okay, so this is also true, this is also true. And also another one is that we can also write for solution, if the reaction is in solution form, or if the reactions occur in solution, or they are the reactant and products are in liquid form, then what we can write, we can even calculate their concentration. Okay, instead of pressure of that reactant and product, we can calculate the concentration. Okay, by using some chemical method. Okay, or using even by doing some titration also, we can calculate the concentration. Potentiometric titration also we can use, or we can even use some conductance measurement. Okay, so concentration can be known. So in such cases, mu I is equal to actually mu I naught plus RT ln, in place of p we can write the ci. Okay, in place of pi. Okay, so here what we can write, in place of p, we can just write the concentration, but concentration is written like this one, m to the concentration of m is this one, symbolized like that. So what we have to write, m to the power m to the power n to the into n to the power n, a to the power a, b to the power b is equal to, but here it will be your k, it is your k c, it is your k c, because it is constant. But previously we write here c na, it should be x. Okay, kx. Okay, so it is your kc. So this is also your law of mass, law of chemical equilibrium. Actually from the law of mass action we derived this one previously. Okay, so I think you understand up to this one. Now coming to the last point. Okay, so coming to the last point, here we have actually discussed or we have derived these relations for actually for this one, actually for real gases, not real gases, ideal gases. Okay, in which actually PV is equal to nRT, PV is equal to nRT formula is applicable. Okay, but for real cases, for real gases, we cannot use this one, because pressure, in place of pressure, we have to, you know, we have to replace this pressure term by fugacity actually. Okay, in case of real case. So here actually, okay, so here actually two relations are given for real gases. Okay, so for real gases, the K, that means the equilibrium constant, it is also known as thermodynamic equilibrium, is replaced by the activity at am to the power am a n to the power a, where a represent what? Activity. If you because in place of the concentration, for the real solution or real cases, we have to replace them by activity. Okay, so that means in place of the concentration, we have to replace them by activity. A is the activity. Okay, this is for real, okay, real gases, and this is for ideal. And the pressure should be replaced by the fugacity. Okay, so here this just replace the pressure by fugacity. Okay, so it is f means fugacity. Okay, fugacity. Okay, and a is what? Activity. Okay, so again we know that your fugacity and pressure is related. Fugacity is what? Fugacity is used in place of pressure, no? So and they are actually related. They are related by relation, which is actually F is equal to P gamma, pressure into gamma, and this is actually your fugacity coefficient of fugacity. Okay, so just here for Fi, you can use also I, because for I component. So you can also use these relations to here you have this kf na, here kf, so this one, so you can replace the value of fugacity by using this relation. Okay, so they use this relation and this relation, then they just get this relations, and from these relations they solve this relation, and they get kf is equal to k gamma kp. Okay, so this is also an important equation, and maybe, but maybe it may come in exam, but the actually the derivation is more important than this one. Okay, so I hope you understand the derivation part of the the law of chemical equilibrium, and it is very interesting, no? So try to understand it, and if you have any idea, then you can write to me. Okay.